Okay, let's get started with chapter 8, Dynamics of Open Chain. Okay, the motion of open chain robot are considered taking into account the force and torque that cause the motion. Okay, so if we apply the force and torque to the robot, at that time we can get some motion of the robot system that can be described using some equation that is called as equation of motion. Okay, just as distinction was made between the robot pole kinematics and the inverse kinematics, it is customary to distinguish between the robot pole dynamics and inverse dynamics. Okay, you should be good at the concept of two kinds of dynamics. Okay, in the case of the equation of motion, like this, equation of motion is described using the second order differential equation. Okay, in this case, the inverse dynamics is the problem of finding the joint torque and the force corresponding to the robot state and desired acceleration. So if we apply the theta and theta dot and theta 2 dot, then you can get the generalized force or torque here. This equation is called as inverse dynamics. Actually, inverse dynamics is used to apply the control to the robot system. So many control concepts making use of the inverse dynamics. Actually, the controller is applied to the acceleration. Okay. Later, maybe the chapter 11, we will talk about how to design the control using the inverse dynamics. Okay, you should mark in mind the inverse dynamics is used for control of robot system. Okay. Okay, the pole dynamics is the problem of determining the robot acceleration given the state and the joint force and torque. So if you rewrite the equation of motion like this, theta 2 dot, as a result, it is called as pole dynamics. So the input will be the theta, the current state, and the theta dot, and the control input. Then we can find out the result as acceleration. And then we will integrate the theta 2 dot to obtain the theta dot, and then one more theta. So next theta and the theta dot can be obtained using this equation. So pole dynamics is used for the simulation of a robot system. Okay, robot dynamics equations are typically derived is one of the two ways. The first one is about the Newton-Euler formulation. Okay, Newton-Euler formulation is well known. Maybe you are good at the Newton's second law. In the case of rotation, the Euler law can be used to derive the equation of motion. Both concepts are combined into Newton-Euler formulation. Okay. On the other hand, if we want to use the energy concept to derive the equation of motion, then Lagrangian dynamics can be used. Okay, we will talk about the two kinds of methods in this lecture. Okay, let's compare the advantage and the disadvantage of both methods. The Lagrangian formulation is conceptually elegant and quite effective for robot with a simple structure such as 2 degrees of freedom or 3 degrees of freedom. But in the case of the 4 degrees of freedom robot system, the Lagrangian method is not effective because the derivative differentiation is required to use the Lagrangian formulation. It will make the problem difficult. Okay, the calculations quickly become the tedious, cumbersome for robot with the higher degree of freedom. Okay, so if we have a robot system smaller than the 3 or 2, then the Lagrangian method will be very effective. Okay. On the other hand, for general open chain robot system, Newton-Euler formulation is very effective, lead to efficient recursive formulation, recursive algorithm for kinematics and dynamics. Okay, so inverse dynamics and pole dynamics can be derived using the Newton-Euler formulation. Okay, actually we can make the mathematics from the Newton-Euler formulation. On the other hand, nonlinear terms or gravity terms can be derived using the Newton-Euler formulation. Okay, section 8.1, Lagrangian. Firstly, we will introduce the basic concept and then we will show the motivation example. The first step in the Lagrangian formulation is to choose a set of independent or generalized coordinate Q. Okay, the generalized coordinate can be used to describe the system configuration. Okay, once the generalized coordinate has been chosen, then the generalized poles can be defined using the power concept of power. Okay, so the one of the generalized coordinate or one of generalized poles is chosen, then the remaining terms will be automatically determined. Okay, so the poles F and the coordinate late Q dot are dual each other. Okay, this is very important. Both are dual. Q dot is determined. Maybe the generalized poles is also determined. Okay, let's take an example. If you use the linear actuator, maybe the poles will be the linear poles. Okay, so the inner product of the linear poles and the linear velocity will result in the power. Okay, if you choose the rotational velocity, rotational speed, at that time the torque can be chosen as a generalized poles. Okay, so you should mark in mind the inner product of power, inner product of the generalized coordinate and the generalized poles will be the power. The Lagrangian function is defined as the kinetic energy minus the potential energy. Okay, the minus is used to derive the Lagrangian. Lagrangian is the scalar quantity. Okay, it can be negative because the kinetic minus potential. Okay. Okay. Actually, in the dynamics course, the Lagrangian formulation can be derived using some optimization, variational principle. So by applying the optimization, we can obtain the following equation motion. Okay, it is called as Lagrangian formulation. The first step is to define Lagrangian, and then round L, round Q dot should be derived, and then we will take the time derivative. Then the minus round L, round Q should be applied. Okay, it will be equal to generalized poles. If you choose the ith coordinate, then ith generalized poles will be chosen. Okay, let's apply it. Let's make a motivation example. Okay, the particle or point mass concentrated on the point M is applied in here. Okay, let's it moves upward using the positive direction x. Okay, let's apply the force F. In this case, the gravitational force is automatically applied. Maybe E terms will be the mg. Okay, so by using the Newton's second law, the inertial force, inertial force is equal to sum of external force or torque. Okay, in here, inertial torque will be the mx2 dot is equal to external force is composed of the two terms F minus mg. Okay, because we choose the general coordinate x going upward. Okay. Okay, this is the Newton's second law. Okay, let's take the example of Lagrangian formulation. Okay, in this case, the kinetic energy will be the 1 over 2 mx squared. Maybe you know this concept, kinetic energy. Kinetic energy is proportional to the velocity square. The potential energy is described mgx, is it right? mgh. H is corresponding to x here. So Lagrangian is obtained as a minus from the kinetic to the potential. Okay, let's apply it. Round L, round x dot. So maybe this term will be the mx dot. Is it right? Because the scale will going forward and then the both are cancel out each other. Okay? Then we will take the time derivative. Maybe the m is the constant, so mx2 dot appear, and then minus round L round x. Maybe the minus mg appear. Is it right? It is corresponding to the generalized force. So we have the same equation. So result should be equal each other if you apply any method. Okay, the example is extended to the two-link manipulator. Okay, here's 2R, 2R. The level joint here and the level joint here. Okay, let's assume that all the mass is concentrated on the end point of the link because it will make the problem to be simple. Okay, so M mass is concentrated here, M2 mass is concentrated here. So length will be the L1 and the L2, and then the general coordinate theta 1 and the theta 2 are chosen. Both theta 1 and theta 2 will be used to describe the equation of motion of this two-link manipulator system. Okay. Okay, the gravity can be chosen as a minus y direction. Okay. And okay, let's take let's calculate the position of endpoint of the first link, x1 and y1. Maybe the x1 will be obtained using the projection to the x direction. So L1 cosine theta is obtained. In the case of the y1, will be the L1 sine theta 1. Okay, and then in order to obtain the velocity of x1 and x2, so let's take the example. L1 is a constant. Cosine, the derivative of the cosine will be the minus sine and theta dot. So theta dot is separated, then we can get these two terms. Okay, well, the end point of the link 2 is obtained using the 2 sine and the 2 cosine. So L1 cosine theta plus L2 cosine theta 1 plus theta 2, because this angle is a theta 1. So sum of the theta 1 and the theta 2 will be used to describe the L2 end point of the L2. Okay, the Y2 is obtained the L1 sine theta 1 plus L2 sine theta 1 plus theta 2. If you take the time derivative, then you have the 3 terms. So if you collect the 2 terms related to the theta 1 dot, then you have the first 1 by 1 element and 1 by 2 element related to the theta 2 dot, and then 2 terms related to theta 1 dot and the theta 2 dot. Actually, this is called as Jacobian. Is it right? Okay. So if the joint coordinate theta are chosen as the general coordinate, at that time generalized force should be equal to the joint torque to make the power. Is it right? So you should mark it in mind. All the time, general poles should be chosen according to the quantity of the joint generalized coordinate. Okay, maybe you know the Lagrangian. Lagrangian is composed of the kinetic minus potential. Okay, it has a two point mass, so it has two terms. So in the case of the link 1, mass 1, the kinetic energy is obtained 1 over 2 m1 x1 dot square plus y1 dot square. Okay, x1 dot is equal to L1 sine zeta 1 dot. So if we take the squares operation, you can get it, and y dot, y1 dot square. You know the sine square plus cosine square will be the 1. So it can be rearranged as a simplification. Okay. On the other hand, x2 dot has the 3 terms. y2 dot is also has the 3 terms. If you take the square operation, then it will provide 12 terms. 12 terms can be collected according to the order of zeta 1 square, zeta 1 dot times zeta 2 dot, zeta 2 square. If you rearrange this equation, then you can get 3 terms like this. And so more simple, much simple way. Okay, let me obtain the velocity of the second term. Okay, maybe you know the linear velocity v1 is obtained using a scalar quantity L1 zeta 1 dot. Is it right? Okay, and then actually the link 2 has the same velocity v1, is it right? And then the perpendicular velocity appears. So it can be decomposed 2 terms, v1 and L2 zeta 1 dot plus zeta 2 dot, because it is the zeta 1. So v1 is the L1 zeta 1 dot. The angle will be the zeta 2. Okay, so 2 vectors can be added using the vector sum. So this term will be the total of velocity. So this vector can be obtained. Okay, v square will be obtained L1 square zeta 1 dot square and L2 square zeta 1 dot plus zeta 2 dot square plus 2 times L1 L2 zeta 1 dot plus zeta 2 and cosine zeta 2. So if you take the square root, then you can get the magnitude of the v. So these terms can be used here. Okay, maybe both are same each other. I'm not sure. Let me check it. Cosine theta 2, L1. If you decompose, I'm sorry. If we decompose this term, okay, let me rearrange one more. L1 square, zeta 1 square, L2 square, zeta 1 dot square, 2 L2 square, zeta 1 dot, zeta 2 dot, plus L2 square, zeta 2 dot square, and the remaining terms are, we have 2 cosine terms. I think we have this equation. I think you can check the correctness, so let me know whether it is correct or not, okay? Anyway, two vector sum of a linear velocity can be used to determine the kinetic energy of the second mass 2. Okay, the link potential energy, it is easy because the height will be the y1 and y2. y1 is the L1 sine theta 1, y2 is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, so we have 4 energy terms. Let's take the Euler-Lagrangian formulation. Okay, these 4 terms, from these 4 terms, round L, round theta 1 dot is obtained. Okay, and then take the time derivative minus round L, round theta 1. Then you arrive at this equation. Please derive this equation by yourself. Okay, it is the best way to practice the Euler-Lagrangian equation. And then the same Lagrangian terms, round L, round theta 2 dot is obtained, and then take the time derivative minus round L, round theta 2. It is more simple. Then you have this equation. Here, according to the order of derivative, such as the theta 1 2 dot, theta 2 2 dot, theta 1 2 dot, theta 2 2 dot, then you can get the matrix and the vector and one more vector. Okay, so if you rearrange the Euler-Lagrangian equation, then mass matrix or inertial matrix, okay, it is called as mass matrix or inertial matrix. In the textbook, it is called as mass matrix. In my terminology, it is inertial matrix. Okay, then the C is related to the theta 1 dot and the theta 1 dot square. So theta 1 dot times theta 2 dot, actually this term is related to the Coriolis torque. On the other hand, theta 2 dot square, it is related to the centripetal torque or force. Okay, this is also centripetal. Okay, so in the case of robot dynamics, the equation motion has the quadratic form in the theta dot. On the other hand, without any derivative, we just get some torque described using the cosine and sine, like this. Okay, so this equation, this G is called as gravitational torque. This equation reveals that the equation motions are linear in theta 2 dot, quadratic in theta dot, and trigonometric in theta. Okay, all kinds of equation motion follows this rule. Okay, let's take time derivative one more. From the x2 dot and the y2 dot, if we apply the time derivative x2 dot, x2 2 dot, y2 2 dot, these two terms can be expanded to the 4 term because it has the product terms, so it can be decomposed to 2 terms, such as theta 1 2 dot and sine theta is replaced with the cosine theta 1 and theta 1 dot, so theta 1 square appear. Like this, we have the 4 terms. Okay, accelerations are expressed as a sum of the terms are linear in the second derivative of joint variable theta 2 dot, quadratic the first derivative of the joint velocity theta 1 dot transpose theta dot, theta 1 theta dot. Okay, so we should mark in mind the acceleration is dependent on the theta dot transpose theta dot and linear in theta 2 dot. Okay, as mentioned before, theta 1 dot square are called as centripetal term. On the other hand, quadratic terms containing theta 1 dot and theta 2 dot like this, j and I are different to each other, at the time this acceleration is related to the Coriolis term. Okay. One more, if you take the zero or angular acceleration, it does not mean the zero acceleration of the mass, because centripetal and the Coriolis terms exist. Okay, let's assume that theta 1 is 0, theta 2 has chosen 90 degree. At that time, the sine theta 1 will be the 0, cosine theta 1 will be 1. Sine theta 1 plus theta 2 will be the 1, cosine theta 1 plus theta 2 is 0. And then we will apply the 0 angular acceleration from here. So 0, 0, and 0, 0, 0, 0, and the cosine will be the 1, sine will be the 0, so this term disappear. Maybe the sine 1, 2 is the 1, cosine 1 will be the 0 and the 0. So we have just two terms. Okay, in the viewpoint of the acceleration of the mass. Okay. Okay, we have just two terms. Let's expand the second term. Okay, the theta 1 dot square plus 2 times of theta 1 dot, theta 2 dot, and the theta 2 dot square. Okay, according to the centripetal and Coriolis terms, we will decompose acceleration vector into two terms like this. This is the centripetal, this is the Coriolis terms. One more, the centripetal term can be decomposed according to the theta 1 dot and the theta 2 dot. So theta 1 dot here, theta 2 dot is here. Okay, the first vector is related to the centripetal term of the theta 1 dot. Okay, let's assume that this structure is stationary. Here, theta 1 dot is applied. At that time, the centripetal term of the proportional to the theta 1 dot square, one more. So two terms can be combined. Then we have this centripetal term. It is related to this one. Okay. One more. The theta 2 dot is applied. Then only one minus y direction centripetal term appears. So we will have it. Okay. And one more. The centripetal terms is related to the minus y direction in the case of the positive theta dot. Okay. If you choose the theta 1 dot as a negative, theta 2 dot as a positive, at the time the outside Coriolis term appear. Anyway, if you choose the positive theta 1 dot and theta 2 dot, at the times minus y direction Coriolis term appear in this acceleration like this. This figure shows the centripetal term acceleration two terms. Is it right? And then Coriolis acceleration. Okay, the Coriolis acceleration appear from the combination of two kinds of rotational motion. Okay, so just you have the 1 degree of freedom motion. There is no Coriolis terms. Okay, but the link is serially connected. At that time, the Coriolis term will be effective. Will be one of the major effects. Okay, till now we have talked about the concept of dynamics. So this Lagrangian formulation will be extended to the more general form. Okay, general formulation for general. Okay, general n-link open chain. All the time, we should take the first step to choose the generalized coordinate. We will choose generalized coordinate theta. Okay, it can be the linear displacement or rotational displacement. It depends on the situation of robot system. And then once theta has been chosen, then generalized poles automatically identified according to the concept of the power. Is it right? And the next step is to formulate the Lagrangian. Do you remember the Lagrangian? Lagrangian is obtained. Lagrangian is defined as a kinetic minus potential. Okay? For rigid body, rigid link robot, the kinetic energy can be written using the inertial matrix or mass matrix like this. Okay, maybe if you are good at the mass matrix, okay, let's write down. Maybe if you take the 2x2 matrix to two-link manipulator system, maybe it will be equal to 1 over 2 set m11 theta 1 dot squared 1 over 2 m12 theta 1 dot and theta 2 dot plus 1 over 2 m21 theta 1 dot theta 2 dot plus 1 over 2 m22 theta 2 dot squared. The inertial matrix is the symmetric, so both are same each other. So it can be added into here, okay, by removing the second term. Okay, let's rearrange this equation. 1 over 2 m11 theta 1 dot squared m12 theta 1 dot theta 2 dot plus 1 over 2 m22 theta 2 dot squared. It will be equal to the kinetic energy of a two-link manipulator. Okay, it can be written using the two kinds of summation. Okay, it must be the generalized form of kinetic energy. Okay, here let's take the Lagrangian from the 1 through the last element of the n. At the time, okay, take the time derivative, take the round L, round theta dot. Okay, let's take it. The 2 will be appear at the front side, so m11 theta 1 dot. Okay, how about that? This one is the plus m12 theta 2 dot. And then we will take the time derivative. Maybe these terms are function of theta, so it should be, the chain rule should be applied to here. Okay, like this, we can get the generalized form of result. This is the inertial related term, linear terms of theta 2 dot. This is the centripetal and the Coriolis terms in quadratic form. This is the potential energy related term. Okay, actually it implies the gravitational torque or force. Maybe you know the m. M is the ni times j element of the inertial matrix. But this gamma, maybe you have seen it for the first time. This gamma is called as Christoffel symbol of the pulsar kind. Okay, Christoffel symbol is the third order tensor. Maybe you have never heard about the tensor. Okay, let's give some concept. Zeroth order tensor, what is that? Scalar. Okay, first order tensor, what is that? Would you estimate it? Okay, vector. Second order tensor, what is that? Please expand. The vector will be the matrix. Okay, third order tensor. There is no name in this case, but the scalar is the point, vector is the line, column, matrix is the square. The third order tensor will be the Q. Okay, the numeric data can be contained in some Q. So this is the n-dimensional, this is the n-dimensional, the depth will be the n-dimensional. So the Christopher symbol can be written n times n tensor. Okay. Actually, this is definition of Christopher symbol. Actually, it is only dependent on the inertial matrix. Mij should be differentiated with respect to the theta k. Mik with the theta j. Minus mjk with respect to the theta I. So 1/2 is taken like this. This will be used to describe the centripetal and Coriolis terms like this. Okay. Okay, this shows that the Christopher symbol are derived from the inertial matrix. Okay, actually, every terms in the dynamics is derived from the inertial matrix or mass matrix. Okay, as mentioned before, round p round theta is can be defined as a g gravitational torque. We can see explicitly the Coriolis and the centripetal terms are quadratic in the velocity by using the form. So actually, if you want to emphasize the Coriolis and the centripetal terms are quadratic, at the time the theta 1 dot transpose and the theta dot can be multiplied front and the lateral part. Okay. So if you write down this equation, you should mark in mind the gamma is a third order tensor. It's a matrix. It's a cube. Okay, n times cube. Maybe you know the concept of the cube. The product of the theta dot transpose gamma theta dot, the result will be the vector, because 1 times n, and n times n times n, and n times 1. So both are cancelled out. The n-dimensional vector remained. So the n-dimensional vector will appear, okay, as a column. So actually the first element will be the theta dot transpose gamma 1. Maybe gamma 1 is equal to gamma 1 jk. Okay, j will be chosen as a 1 through times n. K is chosen 1 through times n. Okay, so it is equal to matrix. So matrix is here. The vector are multiplied each other, front and the lateral part, it will be the scalar. So we have the n-dimensional scalar. It is corresponding to the column vector. Okay. Okay. Almost every robotics textbook, maybe the dynamics is written like this. Okay. In here, these two terms can be replaced with the C matrix. Okay. This matrix is called as Coriolis and the centripetal matrix. Okay. As mentioned before, you can get a definition of the C. Cij is the i's column, j's row element of the C matrix. Okay, this kind of Coriolis and the centripetal matrix is used to prove the passivity property. Okay, the passivity property is very important.
웹에서 다음 결과를 찾았습니다.
I'm sorry, the Siri is responding to my saying. Okay, I'll close the notebook or laptop. Okay, so next to proposition 8.1, we'll introduce the m-2c as a skew symmetric matrix. That definition will be utilized in proving the stability, global stability, or the asymptotic stability. Okay. Later, this concept will be utilized to write down, to derive the control law. Okay. Okay, the proposition 8.1 is very important for the control theory, m dot minus 2c, the result will be the matrix m by n. It must be the skew symmetric. Maybe you know the skew symmetric. Skew symmetric case, the diagonal all the times are 0. The off-diagonal terms as chosen first as a 1. The corresponding off-diagonal term will be the negative. It is called as skew symmetric. Okay, so in order to be the skew symmetric matrix, the diagonal terms should be 0. Okay, the m dot minus 2c, the n ith row, jth column component of this matrix can be written using the Christopher symbol. Okay, the m dot, if you take the chain rule, round mij round k, and then k dot is chosen. So this terms is corresponding to the m dot ij. And then the remaining 3 terms are chosen, derived from the Christopher symbol. Here, you can know that first term and the second term are same each other. So both terms are same. If we exchange the position of this element, round mjk, round theta I minus round mik, round theta j, and then the theta dot k is multiplied. Okay, here, if you change I go to the, if you with the j is replaced with the I. At that time, the both are exchange each other, so negative sign is required. It means if you take the negative, then this will be the plus and the minus. So the minus sign is applied like this, then we have the same matrix. Is it right? So m dot minus 2c must be the skew symmetric. It means transpose of the m dot minus 2c is equal to minus. Okay? In other words, the diagonal term of this matrix is 0. The off-diagonal terms has the opposite sign each other. Okay, please mark in mind, m dot minus 2c is skew symmetric. Okay, the 8.1.3, understanding the mathematics. Maybe you are good at the ellipsoid concept, so we will review it as fast as possible. Okay, maybe you know the kinetic energy, 1/2 m dot transpose m, theta dot transpose m, theta dot. Actually, it is generalized version of 1/2 mv squared, is right? For the point mass. Okay, here's, in order to understand what the inertial matrix means, let's take the acceleration ellipsoid. If you choose the theta 2 dot square as a 1 unit circle, maybe the theta 1 2 dot, this is the theta 2 2 dot. If you take any value according to the according to the angle using the same radius, if you take any value of the surface of a unit circle, it can be multiplied to the inertial matrix. Okay, maybe the cosine and sine. Then it is corresponding to the ellipsoid. This ellipsoid can be written using the major axis and the minor axis. So some acceleration, the unit magnitude and some direction will make the big torque in some direction. Is it right? So in order to obtain this kind of concept, we should apply the eigenvalue decomposition to the inertial matrix. Okay. So for the easy understanding, we will choose the numerical value as 1, L1 as 1, L2 as 1, M1 as 1, M2 as 1. Then we can get the inertial matrix for the second, two kinds of computation. It depends on the computation. The same element computation is different. At that time, inertial matrix is also different. As you can see here, the unit ellipsoid of acceleration is chosen. That relatively small size was ellipsoid-like. The torque ellipsoid appeared. So in this case, joint torque experienced with the similar torque in the irrespective of the direction of the tau 1 and the tau 2. Okay. So it is greatly dependent on the computation of the robot. Okay. The direction of the principal axis of the mass ellipsoid are given by the eigenvector Vi of the inertial matrix, and the length of the principal semi-axis are given by the corresponding eigenvalue. So eigenvector and eigenvalue of the inertial matrix or mass matrix will produce the major axis or minor axis of the torque ellipsoid. Okay. Okay, it is easier to visualize the mass matrix if it is represented as an effective mass of the end effector, because it is possible to peel this mass directly by grabbing and moving the end effector. Okay, let's assume that. Okay, robot is located here. If you grab the end effector of the robot system, then if you move by grabbing the end effector of the robot, if you push the robot and pull down like this, you can feel the pulse of end effector. It depends on the inertial matrix. Okay? So if you grab the end point of the 2R robot system, depending on the direction you apply the pulse to it, how messy would it feel? Okay, it is example. It is the issue of haptic display. Okay, so let's assume that let's denote the effective mass matrix at the end effector as a lambda, and then we will take the task velocity of the end effector as a v. Okay, actually the energy is a scalar value. Energy is independent of the coordinate. So 1 over 2 m dot zeta dot transpose m zeta dot is equal to 1 over 2 task space velocity, task space inertia, and task space velocity. It is independent of coordinate. It is respective regardless of the coordinate. So both values are same each other, because the physical system is the same. Okay, assume that the v end effector velocity is related to the Jacobian j zeta dot. So it will be applied to here. Okay, then it is applied to here. Okay, J inverse v will appear both sides. And then if you take the transpose operator, then you can get the inner part. J inverse transpose m J inverse. It must be equal to end effector inertia. Okay? So end effector inertia is obtained. J inverse transpose m J inverse. Okay, if you know the Jacobian and the joint inertia matrix, then lambda can be calculated using the small calculation like this. Then if you apply the unit circle of linear acceleration x 2 dot and y 2 dot, then some false ellipsoid is obtained. Okay, let's reinterpret this equation. Okay, some direction of x to okay, in here the y direction is chosen. Okay, here maybe the x to dot as a 0, y to dot is chosen as a 1. Then 2 times of force appear at the end effector. Okay. One more. Also, both are dependent on the configuration. Okay. Figure shows the end effector mass ellipsoid with the principal axis direction given by the eigenvector of the lambda and the principal semi-axis length given by the each eigenvalue for the same 2 kinds of 2R robot configurations. Okay. The endpoint accelerations are scalar multiple of the poles applied at the endpoint only if the pulse is along a principal axis of the ellipsoid. Unless lambda is of the form such as the C constant of the inertial identity matrix. Okay, here the mass at the endpoint feels different from the point mass. Okay, this kind of issue is subject is such topic of haptic display. This is another academic field related to the robot system. Okay, the Lagrangian dynamics and the Newton-Euler dynamics are compared each other by taking a simple example. Okay, the next section will be related to how to derive the Newton-Euler equation using the iterative method. Anyway, let's summarize the 8.1.4. Using the tool we have developed till now, the Newton-Euler formulation allows computationally efficient computer implementation, particularly for robots with the many degree of freedom without need for differentiation. So, if we wanted to apply the Newton-Euler formulation, there is no need, there is no differentiation because we will insert differentiation in advance. The resulting equation of motions are identical with those derived using the energy-based Lagrangian method. Okay, so either way can be used to derive the equation of motion, such as the Lagrangian and the Newton-Euler. All the time, results will be same each other.